What's going on, everybody? Johnny Bannon here at Trepa Technologies. In today's video, we're going to be going over domain 1.6 of our Network Plus N10-009 full course. So this is going to be compare and contrast network topologies, architectures, and types. Let's go ahead and get started. So I'm going to move my face out of here, just zoom it out just a little bit. So here's our objectives. So we're going to be going over, again, network architecture. So we're going to talk about a mesh, star and hub and spoke, spine and leaf, point to point. Go over our campus networks, which is our traditional like 3-tier topology, and then how we collapse that. And then last, we're going to talk about is traffic flows, which becomes very important in today's day and age of networking. I mean, we have cloud networks, we have software-defined networks, we have very large campus networks that, with the use of VXLAN and Lisp, DNA Center, right, our software-defined stuff, where traffic may flow east to west at like that leaf level. Our segmentation may flow east to west on our access layer. We may have micro-segmentation in the cloud, which flows east to west. Kind of different than what we may be used to in a typical, basic, traditional on-prem environment. So first thing we're talking about is mesh. So a mesh topology is just when, a full mesh is when every single node in that environment, whatever computing environment you're in, is all connected to each other. There's full redundancy. So every node is connected directly to every other node in the network. So obviously high-level redundancy, and with this sometimes comes some complexity. Depending on what type of computer network we're talking about, like just for example, a basic layer 2 topology, we would need something like spanning tree enabled here so we don't end up with broadcast storms. If this was all routers running OSPF on a Ethernet segment, we would have that be a broadcast network and there'd be a designated router. Because with all that redundancy, all those connections, we want to avoid loops. So something OSPF does is elects a DR and a BDR. In some of our routing protocols, we may have, in this environment, something called split horizon, which is like it loops. So full mesh provides full redundancy, but also some complexity. Lots of cables, lots of additional configuration. And again, all depending, it could cost you a little bit more because of the complexity and really how many nodes you would have to purchase, right? Then we have a partial mesh. This is just where some nodes are connected to multiple nodes, okay? While others are connected to maybe just one or two. So you can see here in this example, this switch right in the middle is connected to all of them, right? Where this switch is connected to this guy, and this guy, but missing this connection. So we have kind of that central point that's maybe connected to all of them, and then some of the other nodes are not. They have lots of redundancy, but not to every single node. This is not a hub and spoke topology, though. This is not hub and spoke. This is a partial mesh, where you will have some of that redundancy you may get with full mesh. Okay, then we have a star or hub and spoke topology. So a star topology, also known as a hub and spoke, and I mean, I've never called anything a star topology, and this is a hub and spoke. They are the same according to the Network Plus exam. But you know, when you're working at big enterprises, you set up DMVPN, Flex VPN. When you're even doing like SD-WAN, there may be some sort of hub and spoke architecture. Now with SD-WAN, it's not meant to be one central point, but we all connect to like a vManage or something. So anyways, there is still that kind of architecture, but there's centralized control where every spoke is connecting to one central node or computer or router switch. So you can go to that router and switch and have that connectivity, that transitive kind of network. Now the downside is you may be left with a single point of failure. If that hub goes down, then all the spokes lose connectivity to each other. And then I'm not going to say it's a brand new architecture. Probably in the Network Plus exam, it may be a little bit new. But we have the spine and leaf topology. So spine and leaf topology has been in the data center for a while. And this is to support those high throughput, high redundancy networks that have enabled software-defined networking in our data centers. And what it makes up, or really the core of it, is that spine layer and then those leaf layers connected to the spine layer. So spine and leaf topology is a modern network architecture commonly used in data centers. If you like go to Aruba, Arista data centers, or Aruba, excuse me, they kind of took over this, right? They kind of were not to say the forefathers, because a lot of these architectures, designs are kind of in academia, and then they get pushed down to like the corporate, and then they implement it. But anyways, that's how they took over a lot of the data center space away from things like companies like Cisco or Juniper. By implementing this spine and leaf layer, you kind of get, you get rid of things like spanning tree, you get rid of some complexity, and you get that low latency because every single leaf switch is always one hop away from each other. So the leaf layer, this is composed of switches that connect directly to servers and storage devices. So that'll be where your server farms, where the data center compute and storage connects to. Then that spine layer is going to be what you would think of with like those core switches kind of in traditional networks, those big beefy switches, high performance switches that connect to all the leaf switches. So with every leaf switch always being one hop away from each other, from any device in that leaf or that spine, you get consistent latency. So when it says low latency, yes, that's true for the backbone network, but you also get consistent latency. So in a software-defined data center or network, if we're pushing configuration to hundreds of devices all at once, having that consistent latency is important, right? When you push a profile down to that leaf layer, and every single switch should get it, we want every single switch to get it around the same time. So use cases. Spine and leaf architectures are popular in data centers, cloud environments, and large enterprise networks where high performance and scalability are critical. Then we have point-to-point. So even though I have hub and spoke up here, let's not get like complicated. What I want to show you with that point-to-point is if we were to kind of take out the secondary connection over here. So let's just say we get rid of this, right? What we're saying here with this point-to-point is that's a leased line. That is, hey, I am buying from my ISP, from my internet provider, a dedicated circuit or dedicated line straight to this router, okay? So even if this is a hub and spoke, what I have here, spoke, Phoenix, Denver office, that Phoenix to Denver office is still a point-to-point network from this perspective, right? Now, and the reason I like this design is because you can see how a point-to-point network could easily become a hub and spoke network where we say, okay, but now we want a dedicated line, and I'm going to erase this, but now we want a dedicated line maybe from the Houston office to that Denver office. And then all of a sudden that Denver office was maybe where we started out. We're like, well, that is where we have our most resources. Okay, now we're going to have some sort of transitive network here, right? But that's still a point-to-point leased line, okay? So they're a dedicated link, they're simple and fast, and in of themselves, right, like if I just lease a T1 line, from the perspective of this Phoenix office, it's really simple. I'm probably just going to, if I have no other ISP connection, the hub is my way out, I'm just going to do like a default route straight out to that leased line, straight out to that point-to-point network. Okay, now let's go over the three-tier hierarchical model. I call this, a campus network. When I first got into networking, I worked in a NOC, finally at the tier 3, tier 2 level, working on the core distro and the routing layers, which is not seen here, right? This is what we call our campus network. Three-tier topologies, what Cisco calls it. The Network Plus exam is calling it the three-tier hierarchical model. So in this model, we have 3 layers. We have the core layer. That's the high-speed, high-capacity Cisco line, like the Catalyst 95, 9600s that are robust. Lots of compute, lots of port density with high throughput, high bandwidth links, and they're going to be the backbone of the network. Even though I have a switch up here, which is typically these layers, are switches, this core switch right here could have like twin ax 40 gig throughput ports connected to downstream, and then upstream, it could be a router here, or it could be straight to the ISP. That core layer could go straight to the ISP, okay? And so that's the backbone of the network. And then we're going to have complex routing here, right? So either that's to a router when we have that like probably a layer 3 connection here, or we're going to have that direct connection to the ISP, maybe connecting us off to a larger enterprise. Maybe we're doing some IPsec, some DVPN, Flex VPN from here at our our upstream to the WAN. And then our distro layer, that's going to act as the intermediary between the core and the access. And this is going to be like the workhorse of the LAN, of the actual campus network. So pretty much if we want to cut this off right here, we'd say down here, downstream of the distribution layer, This is going to be where all the filtering is happening for our users, all of our switch virtual interfaces, the layer 3 routing for our users is happening. This is where we're going to have ACLs, VLAN access control list. Well, that may be the access layer, but this is going to be what's controlling and doing the routing for our users in our campus network. If we have enterprise resources and servers on-prem, we're connecting it to this distro layer. If we got domain controllers, we got things like maybe, collaboration tools, collaboration servers, like Call Manager. We're going to have that at the distro layer. So our server farms, our data center servers, compute and storage resources are typically going to get out to our campus, our enterprise, through the distribution layer. And okay, it has quality of service on there too. Sorry, sometimes I don't read the slides fully. And then we have the access layer. So this is where you're going to have the users. You're going to have all of our endpoints that aren't servers, right? Now, of course, you could hook up like maybe a tower server here, but a good architecture with a good NetOps team, you're probably not going to do that. This is where our endpoints are, our VoIP, our workstations, also our access points. So our access points, right? Maybe our lightweight access points can be controlled by a wireless LAN controller up here. And the access points themselves, the ones sending out that Wi-Fi RF signal for our Wi-Fi enabled devices, are going to be connected to that access layer. So common use case, this is going to be a large enterprise. This is a large campus network. We're a big company, 10,000s of users, thousands of users and above, and maybe multiple different geographical areas. And we build out a 3-tier core topology to give us lots of redundancy and lots of complexity, but in a good way, right? Where we can have a lot of customization for maybe our unique work cases. And then we have the collapsed core model, which you're going to notice looks a lot like the 3-tier model, and it is, except it's for smaller. So this is going to be for those enterprises that aren't as robust, that don't have those tens of thousands of users, but maybe we're used to kind of making that campus network. We still have some sort of robustness to us, maybe a small to medium-sized business with minimal growth, but we want those beefy switches. We want to be able to have high availability, so we say, hey, we don't need that additional core and distro layer. We'll collapse that. We'll have the core and the distribution layer all in one, directly connected to the ISP, right? Or again, it could be to like another router. And then that's going to be where we hook up servers. That's going to take on the role of the core and the distro layer. And then the access layer stays the same. All of our endpoints, access points, computers, printers, VTC machines, whatever endpoints we have are going to still connect to that access layer. Okay, now let's go over traffic flows. So this is a great, to me, a great example when we even go through spine and leaf and then to the 3-tier, how traffic could flow. So in north to south traffic, this is going to be something that's typical. It's going to be standard where we have some sort of default gateway here that is needed. We have to come up to that default gateway to come back down to talk to our other devices, and segmentation kind of starts there, right? Think of this as like a router on the stick implementation where each device down here, I'll put this in a different color, is in its own VLAN, so its own broadcast domain with its own subnet. So we'll put 10.0.0/24, and over here we have 10.0.0, we'll go back, .1.0/24, and we still have that default gateway, and here it's a switch. This could be representing like a router here that has now those sub interfaces that are doing that network segmentation for our traffic. So when I'm a user in VLAN 10 and I gotta talk to VLAN 20, a different broadcast domain, a different network, I send traffic to the default gateway north, and it routes it back down south to that. And that's where we apply security policy, right? North to south. Now east to west, that would be traffic that maybe flows within the same data center. So what we mean by that is instead of having, like, this could be a software-defined architecture, even in the cloud, that software-defined networking in the cloud, where imagine this is like in Azure cloud, this is the example I'm going to kind of use, but this is a VPC, or what we call a VNet. And we have what's called subnets in the cloud. This is the subnet 1 with 10.0.0/24, all in that same VNet. And this is in subnet 2, and this is 10.0.1.0/24, And instead of us going to some central default gateway like a router on a stick environment in this software-defined network, we're just going east to west. And we may apply security policy directly to those devices. And we have that kind of what we call microsegmentation, and they just talk directly to each other, those compute nodes, okay? So communication between devices in the same environment. Hopefully my handwriting wasn't too bad there. Okay, now let's go ahead and do our quiz. Okay, let's go ahead and do our quiz now. So I'm going to come here to our Network Plus course. I'm going to come to quizzes, and we're going to go to domain 1.6.1. And let's go ahead and get started. I'll move my face down here in case I want to clip it. So, what is a major limitation of a point-to-point topology? So, let's actually think about this one here. So I did show us that in a point-to-point topology, you could kind of technically scale it out, right? You could scale it out to the point where now all of a sudden a device that was just point-to-point now becomes a hub. Your enterprise is expanding. One thing I didn't mention there is that point-to-point, it is expensive, but it's not because of extensive cabling. You could, if you just want a dedicated circuit, it can get expensive though. So limited scalability. There is limited scalability when it's just point to point. We can show our explanation here, and there we go. Okay, question 2. What is the primary advantage of using a full mesh topology in a network? That's going to be the high level redundancy. Definitely not the reduced cabling. So we see our explanation here. Question 3. In a star topology, what happens if the central hub fails? So it's not going to be C, it's not going to be D. I'm going to put the entire network becomes inoperative, but let's read A here. The only the devices connected to the failed hub are affected. Now, obviously, I think what this question is trying to say is like, it's trying to get you to think like, no, if you're in a star topology, every single user is affected once that main goes down. But obviously, we could be in a star and hub and spoke topology where we have local like flex connect even on Wi-Fi. We can still talk to each other, maybe just not the users at the hub. But I think for the Network Plus exam, I want you to say that everything fails. Sometimes I teach CCNP and CCNA and like sometimes some high-level networking classes, so I'm trying not to go there. This is Network Plus, right? It just fails, okay? If the hub fails. Question 4. Which of the following is a key characteristic of a spine and leaf topology? So let's see. It connects each node directly to every other node. Oh, I read that completely wrong. I was thinking each node to every node, not every other node. My apologies. Yes, it is B. It utilizes high-performance switches for equal bandwidth between endpoints. That is true. That is what spine and leaf topologies do. And I apologize. For some reason in my head, I was like, yeah, it connects to each node. This is a good example of why you need to think before you just answer on the exam too. And in spine and leaf, every node is connected to each other, not every other node. Every node. So, cool. Now it's not going to say 100%, which irritates me. My OCD flares up. Okay, question 5. Because we're going to have red now. It should be all green when we finish. In the 3-tier hierarchical model, what is the primary role of the distribution layer? So, doesn't connect directly, merges the core and access layer into one. I'm not going to say it merges it into one. It's kind of the, it's sandwiched. It's in the middle. It's going to enable the access and distro layer to talk. Then implements routing, filtering, and policy-based networking. That it does for our users. So we're going to go with D. Then question 6. What is the main benefit of a collapsed core network design? So it's going to be reduced cost, right? So in collapsed core, we told you that they are literally collapsing the core and distro layers. So that's going to be a reduced cost, right? And the complexity does decrease as well. Let's look at our results. Awesome. So I don't know why. Just if it don't get 100 on here, it's like, it's irritating. But that's okay. good example of why you should read the questions thoroughly and not just be like, oh yeah, connects to every node. It was just in the top of my head. So I want to thank you all for viewing. Don't forget to like and subscribe. Leave a comment below if you're enjoying the content. And leave a comment actually below if you want to see some bonus network material not related to Network Plus. Thank you for viewing. Please share with your friends.